Hey everyone, welcome back to AI Team. In this video, we're diving into tensors, not from a complex mathematical angle, but from a practical perspective. If you're getting into deep learning, understanding tensors is essential. Too often, people jump straight into building models without fully grasping the fundamentals. Then, when things go wrong, they struggle to figure out why. This video is not for absolute beginners, but if you've already started your deep learning journey and want to strengthen your foundation, you're in the right place. Let's get started. What are tensors, and why are they important in deep learning? At their core, tensors are a generalization of matrices, playing a crucial role in deep learning by helping compute outputs and update weights in a neural network. But let's keep it simple for now. Think of a tensor as just a sequence of numbers stored in memory. For example, imagine a list of 120 numbers ranging from 1 to 120. We can also visualize it as a table with one row and 120 columns. No matter how we describe it, the key takeaway is that the total number of elements remains the same, in this case 120. Understanding this concept will help you grasp more complex tensor operations later on. Let's dive deeper. What happens if we turn the list vertically? Instead of one row with 120 columns, we now have one column with 120 rows, a 121 tensor. But here's something important to note. The number of elements hasn't changed. It's still 120 because 120 times 1 is equal to 120. Now, keep this in mind, this vertical representation is purely conceptual. In reality, the numbers are still stored sequentially in memory. We just interpret them differently by treating each number as if it were on a separate line. This idea of reshaping tensors is a powerful concept in deep learning, and it plays a big role in how data moves through neural networks. Let's keep going. Let's go back to our original list, a single line of numbers. Now, what if we group every 6 numbers together? For better visualization, we can reshape it into a table or matrix with a shape of 26. This means we now have 20 rows and 6 columns, where each row contains 6 numbers. But here's the key point. The total number of elements hasn't changed. It's still 120. Now, what if we want to reshape our 26 tensor into a new tensor with 4 columns instead of 6? In PyTorch, this process is called reshaping, and it allows us to restructure tensors while keeping the total number of elements the same. Warning: don't try to figure this out just by looking at the table representation. You'll get confused quickly. Instead, focus on the number of elements. Since we started with 120 elements, we need to find a shape that still multiplies to 120 while having 4 columns. Let's explore how this transformation works. Instead of trying to reshape the table visually, let's go back to the basics. Start with the original horizontal sequence and group the numbers into sets of 4. By doing this, we can quickly determine that the new shape will be 30 rows and 4 columns, giving us a 30 for tensor. And of course, the total number of elements remains the same. 30 times 4 is equal to 120. This simple approach makes reshaping tensors much easier to understand. Let's keep going. So far, we've worked with 2D tensors, like 30 by 4. But what if we keep the same sequence of 120 numbers and reorganize them into a list of 6 matrices, each with a shape of 5 by 4? This transformation gives us a 3D tensor with a shape of 6 by 5 by 4, where 6 matrices. Each matrix has 5 rows and 4 columns. 6 times 5 times 4 is equal to 120 elements, still the same total. To figure this out, go back to the basics. 1. Start with the horizontal sequence. 2. Group the numbers into sets of 4, forming columns. 3. Take 5 of these groups to form rows. 4. Finally, stack 6 of these matrices together. And just like that, you get a 6 by 5 by 4 tensor. Now, when working with 3D tensors and higher, you can safely think in terms of matrices or tables without causing confusion. Important tip: as long as you don't modify the last dimension, meaning the number of columns, the tabular representation works just fine. However, if you need to change the number of columns, it's best to go back to the horizontal sequence representation. This method avoids confusion and makes reshaping tensors much easier to understand. By keeping this in mind, you'll be able to navigate tensor transformations with confidence. Now, let's take it a step further and move to a 4D tensor with a shape 2x, 3x, 5x, 4. Even though we've added another dimension, the total number of elements remains the same. You can verify that it is still 120. Important warning: you cannot reshape this into a tensor of 3x, 3x, 5x, 4, because 3 times 3 times 5 times 4 is equal to 180, which is different than 120. Whenever reshaping, always make sure that the total number of elements stays the same. Understanding this concept is crucial for handling tensors in deep learning. Let's keep going. Now, what if we want to reduce dimensions by merging the second and third dimensions of our 2 by 3 by 5x4 tensor? By doing this, we reshape it into 2 by 15 by 4. The total number of elements remains the same, we're just reorganizing them. This technique is useful in deep learning when you need to flatten certain dimensions while keeping the overall structure intact. Final example: swapping dimensions. Let's say we want to swap the second and fourth dimensions of our tensor, 2 by 3 by 5x4. After the transformation, the new shape becomes 2 by 4 by 5x3. Always double-check the total number of elements unchanged, 120. Important tip: since we modified the last dimension, it's better to use the horizontal sequence representation to understand the new matrix structure of 5 by 3. This approach makes it much easier to visualize tensor transformations correctly. Now, by stacking the groups of 3 on top of each other, we get a series of 8 5 by 3 matrices. This means we're organizing our data into 8 layers, each containing a 5-row by 3-column matrix. This kind of transformation is crucial in deep learning when dealing with batch data or multidimensional tensors. Now, let's take it a step further. We group every 4 of these 5 by 3 matrices together, forming bags. By doing this, we end up with 4 of these bags, each containing 4 5 by 3 matrices, resulting in a new tensor shape, 4 by 5 by 3. Final step: grouping into bigger bags. Let's take our series of bags and group every 4 of them together. This gives us 2 bigger bags, resulting in a new tensor shape, 2 by 4 by 5x3. Even though we've restructured the data, the total number of elements remains the same, we're just organizing it differently. This step is essential in deep learning when working with higher dimensional tensors and batch processing. Understanding broadcasting in tensors. In deep learning, we often need to perform arithmetic operations on tensors with different dimensions. This is where broadcasting comes in. It allows us to automatically expand tensors so they can operate together without manually reshaping them. For example, consider this operation: 3 by 4 by 2 multiplied by 1 by 2. How does broadcasting handle this? Let's break it down step by step. First, let's start with this simple example, such as multiplying 3 by 4 tensor by a scalar 10. This is an element-wise operation, meaning every element in the tensor will be multiplied by 10. However, this is more subtle than that. Let's see the details. So, how is broadcasting applied in reality? It happens in 2 steps. 1. Broadcast horizontally. The smaller tensor is expanded across columns. 2. Broadcast vertically. Then, it's expanded across rows. This automatic expansion allows tensors with different shapes to operate together seamlessly. When does broadcasting not work? Not all tensor operations can be broadcasted. Some cases are forbidden because at least one dimension doesn't match. For example, 3 by 4 does not match with 2 by 2. 3 by 4 does not match with 1 by 2. In these cases, broadcasting fails because the dimensions are incompatible. Broadcasting rules explained. To perform broadcasting, tensors must have compatible dimensions. But what does that mean? Here's the rule. Starting from right to left, each corresponding dimensions must either be the same or one of them equals 1. For shorter tensors, missing dimensions are considered as 1 for compatibility. Examples of compatible tensors. 2 by 4 by 6 and 1 by 6. Interpreted as 2 by 4 by 6 and 1 by 1 by 6. 2 by 4 by 6 and 1 by 4 by 1. These can be broadcasted successfully. Now, let's look at a more complicated example of broadcasting. 3 by 2 by 4 multiplied by 3 by 1 by 1. How does this work? Following the broadcasting rules, we compare dimensions from right to left. 4 against 1 is valid, since 1 can expand to 4. 2 against 1 is valid, since 1 can expand to 2. 3 against 3 is valid, same dimension. Thank you for watching. If you found this video helpful, please give it a thumbs up. Don't forget to subscribe for more content, and share this video with others who might benefit. We'd love to hear your feedback and suggestions in the comments below.